Also, let me briefly introduce the company I work with. It's Mapillary. So Mapillary is an infrastructure where people around the world can collect data, in particular street-level images. So those are crowdsourced. And we use computer vision to analyze those images. And the images are available for the people that actually also upload them. And our mission is to understand the world from those images. So we perform automatic analysis and make all those results then available. So to date, we have 305 million images collected. They cover 5 million street kilometers. We have 25 billion objects detected. And the images span around 190 countries. And images, we have no control on the images. So those are collected with mobile phones, action cams. We have 360-degree images, dash cams, images collected from cars, and also some images collected with professional rigs. So for us, robustness is very important, just because we have really no control on the quality of the images. We have images going from low resolution to 22 megapixel per image. And one of the important tasks that we address is semantic segmentation, because we use then the results from semantic segmentation for help also other analysis. And so the talk of today, I will just briefly sketch why robustness is important for Mapillary, and then introduce in-place activated BatchNorm, which is a paper that we published this year at CPR, which allowed us actually to get to this result, and finally show some experimental results. So as I said, semantic segmentation is important for Mapillary, and we extract 97 classes from the images. So all the 300 million images have been processed. So we have segmentation for all those images. We extract automatically line features, and semantic segmentation is used also to improve the 3D reconstruction. So we can use the semantics to locate objects in 3D space, and also get rid, for instance, of moving objects when we want to do static 3D reconstruction. The segmentation results have been used to train traffic sign detectors. We have detectors for 1,500 traffic signs, and also for privacy purposes. So we automatically can blur face and license plates. So we come now to the main work that allowed us to get to this result. We call this in-place activated BatchNorm. And the key observation comes from the fact that, so for tasks like image segmentation, we need to have dense predictions. And those typically are very memory intensive. So typically you can fit only a batch size of 1 per GPU, so 1 image per GPU, unless you want to really reduce the crop size or reduce the model. And we noticed, but this is not new, that there is a strong correlation between model performance and the size of the input crop and the depth, of course, of the model. And while there was already a lot of work focusing on optimizing memory at inference time, few of them have coped with the training time. So our goal is really to reduce memory consumption at training time, because this allows us to use larger crops, larger batch sizes, or deeper models to actually perform the segmentation. So the idea behind this work is that, so in a typical network where you have a BatchNorm, an activation function, and let's say a convolution operator. So the convolution is just here for as an example, but the two key components are BatchNorm and the activation. So typically you need for this building block 2 buffers to be stored. While we show that we can actually do the same by having only 1 buffer stored per triplet, like BatchNorm activation convolution. So basically we are able to reduce the memory consumption by more or less 50%. And we show this gains by doing this on modern networks like ResNet, DenseNet, wide ResNet. And the computational overhead that we introduce is really low. It's between 0.8 and 2%. And the layer that we propose is really self-contained, so you can use it as a plug-in replacement of BatchNorm and an activation function. So you can take BatchNorm and ReLU and replace it with our in-place activated BatchNorm and reduce memory consumption by 50%. So you can see here a standard setting where you have a BatchNorm activation function convolution, and the dashed blocks on the top is what you need to store for computing the gradients when you go in the backward pass. So the blue part is the backward pass, and the green part is the forward pass. Okay, I skipped the introduction of BatchNorm, but it's, as you all know, basically you make a whitening of your input based on statistics estimated, so mean and variance estimated from the batch, from the mini batch. And then you have a linear operation to recover the loss of representation power. One standard approach, or alternative approach to reduce memory is checkpointing. So in this, okay, for some reason it's skipped, but the idea of checkpointing is that you store only X in the image above, but then when you need Y, in the backward pass, you need to recompute from X. So you just keep track of X and you recompute, basically in that case, the BatchNorm and the activation to compute the gradient afterwards. What we do is we take a different approach. We rewrite the gradient as a function of Y. We store only zeta, and then we can compute backwards the X hat, which is the normalized input, by inverting the activation function and the linear operator that you have after the BatchNorm, or within the BatchNorm. We have also a second, more optimized version. Oh, I don't know why it's skipped, but the second optimized version does not depend on X hat, but we can make a gradient that depends directly on Y. So basically we have the same memory consumption or memory reduction, but we have even a smaller computation overhead because we don't need to invert the linear operator. So what's written as pi gamma beta. So just to have an overview, so when you have a standard strategy, you need to store the buffer that we call X zeta, then you need to store the BatchNorm statistics. When you have a checkpointing, you need to store X and the BatchNorm statistics, and in the computation part, you need to recompute BatchNorm and the activation function. With in-place ABN, the first version, we just need to store zeta and the variance of the batch normalization. And in the computation part, you need only to invert the activation function and the linear operator. So you have again a linear operator. And the second version does not require the inversion of the linear operator. So we have the same memory requirement, but it's faster in the computation. Now, I will briefly explain what we used for the challenge. So we had a backbone, which is the wide ResNet 38. And we replaced all BatchNorm ReLU with our in-place ABN. And since we need an invertible activation function, we wanted something that is close to ReLU. So we used leaky ReLU with a small slope, so 0.01. And as the head of the computation, we used DeepLab 3. So the output of the wide ResNet had a stride of 8. Also in the DeepLab 3, we replaced BatchNorm and the activation with our in-place ABN and leaky ReLU. So the DeepLab head has 4 parallel conv blocks with different dilation rates. So 1, 12, 24, and 36. And each of those had, in our case, 256 output channels. Then there is a global pooling. And all those, so the 4 parallel convs, the output of the 4 parallel convs and the global pooling are stacked together. And then we have another conv, BN, and in-place activated activation layer. And then finally we get 256 channels, and on top, of course, the classifier. We applied online hard example mining. So basically, instead of taking all the pixels when we compute the gradient, we take only the 25 worst pixels, and we use only those to compute the gradient. This allows to implicitly cope with the balancing of the distribution, of class distribution, but also inner class distribution. So if there are some more difficult tasks, this at some point will be preferred over the simple ones. Moreover, we need to compensate for imbalancing in the distribution of the training data. So what we what we used is a different sampling of the data, which is done in a way that we get roughly uniform distribution over classes at the end of the training. So when you consider the distribution of the classes that we have seen at the end, it's roughly uniform. And the segmentation model above has been fine-tuned on papillary vistas for 90 epochs. And we used, in that case, train and validation data. And finally, we have a train with stochastic gradient descent, standard momentum, polynomial learning rate decay, as you can see. And then we had random scaling between 0.7 and 2, so random. And thank you to in-place ABN, we could keep crop sizes of 776 squared and 3 images per GPU. And the GPU that we used were 4 GPUs Titan XP. Moreover, we implemented in PyTorch a layer to have synchronized BatchNorm. So basically, we are able to synchronize the statistics in the forward and backward pass across the 4 GPUs. And we have, so the code is available, both the in-place ABN and this synchronization of BatchNorm statistics. So one of the, we think that one of the key elements or key that allowed us to get a robust classifier is that we used Papillary Vistas dataset. So this dataset has been released last year. We published this in ICCV 2017. It has 25K high-resolution images. There are different resolutions. It's not just one resolution like in Cityscapes. You can find images with more than 20 megapixels, as well as HD images. There are up to 100 object classes and 60 instance-specific classes, but this is for the commercial version. 66 for the, so 66 object classes and 37 instance-specific for the one that it's available for research. And for the challenge, we trained on the one that is available for research, so the public version, of course. And the dataset covers 6 continents. There are different viewpoints. We have roads, sidewalks, off-road, wide, different types of camera sensors, as I showed at the beginning, because those are really images that were collected by users with their own camera settings, and different weather conditions and capture times. So by training on this dataset, we managed to have a classifier that was already robust to different, to a wide range of images in the street level context. And we were also surprised that this managed also, without any other addition, to get reasonable results on Scannet, okay? Which was the only dataset that had a different set of classes. For the challenge, we trained 5 models that were pre-trained on Vistas, and then fine-tuned on all ROB data. So there were, and only in 2 models, we tried also to put some 1K BBD images in the set. One thing that we did is, and this was the only thing that was allowed to be dataset specific, we applied a scale correction to Kitty. And so we scaled Kitty by 2. So the idea was to have more or less that the size of the cars in the different datasets are more or less the same. And also Scannet had 2 different resolutions. So the lower resolution were upscaled by a factor of 2. Everything else was just, we took all the set together. We extended the classifier to have street level classes and Scannet classes together. And we just trained this without any other tricks. And at test time, we had multi-scale testing by averaging 3 scales, 0.8, 1, and 1.2. For training, we always kept one set out, such that we could have a rough idea what was the performance on the, what could be the performance on the test set. And we did nothing for the void label. So we were always predicting valid classes. There was no setting, no class set to void on purpose. And so this is what we got. We got first rank on Kitty, Scannet, Cityscapes, and WildDash. And some more details. So we managed to get first position on Kitty on intersectional union and on the instance intersectional union. The same for WildDash. And for Scannet, we were first in intersectional union, and same for Cityscapes. So best score in intersectional union and instance intersectional union. So what boosts the instance intersection reunion, actually we found out, is the hard negative mining. So here we have some qualitative results. So summary. So robustness is crucial for our company because we have images really taken without control. And we found out that vistas, mapillary vistas, was good data to pre-train on to actually achieve robustness in the classifier. And one of the key elements that were used was this in-place activated BatchNorm that allowed us to free up 50% of the memory. And therefore, we could train with larger crop sizes, larger batch sizes, and deeper models. And if you want, there is this joint Coco and Mapillary challenge at ECCV. So we invite you to participate. And thank you for the attention.
Hey, we have time for a few questions. I got one question actually. So what's pretty interesting for me is, semantic segmentation obviously works better if you have a wider variety of things in your train sets, right? If you train on multiple of these data sets at the same time, does it actually also help the performance on a single one? Like if you just train, for instance, only on ScanNet and then you train other data sets at the same time, does it help to boost the ScanNet performance if you add in more variety outside of ScanNet?
So we trained a similar model on cityscapes only, and we managed to get to 82%. By having all the models together, we get to 80.5. So I think it depends on the data set. For instance, I think on cityscapes, on the test data, it's closer in distribution to the training data. So, you get better results, but this doesn't mean that, it's a bit, it's not the truth because the real world does not have this distribution. So for Mapillary, we did not try to see what happens on vistas when we take now these models that we trained all together. But of course, for some of the data sets in the challenge, like Wildash, there were so few images that, there was no point actually. We did not even go and sample more often on Wildash. There were so few that the risk of overfitting was very high. So of course, if you have a larger variety of data, you will have a classifier that works better across different data sets. But I don't expect this to get first rank on the specific data set, typically because the test set follows somehow the distribution of the training set.
Okay, thank you. Do we have another question? We have time for one or two more. Okay, if not, let's thank the speaker again and congrats to winning the challenge.
Thank you.